Radix 2 FFT algorithm for n equal to 2, and then the calculation of k from 0 until n minus 1. So we have n minus 1 equal to 1. So we have even function here, where the equation is the summation from r equal to 0 until 0. This one is based on n divided by 2 minus 1. So 2 divided by 2 is 1 minus 1, we have 0. So we just need to calculate for r equal to 0. For n equal to 2 r for even function. So this is w rk. So k equal to 0, r equal to 0. So we have this one for k equal to 0. And then for k equal to 1, and we substitute r equal to 0, so we also have this one. So g0 is equal to g1 for even function. For odd function, from the summation from r equal to 0 until 0, again based on this equation. And then n equal to 2r plus 1 for odd function. And we substitute r equal to 0 and k equal to 0. We have this one for k equal to 0. And then for k equal to 1 and r equal to 0, we also have this function where h0 is equal to h1. So the next one is the calculation for w with the power of k for n point, and is equal to 2. And we have this function. When we substitute n equal to 2, we have exponent negative j pi k. This one based on Euler's identity is equal to cos omega k, cos omega n, or cos omega k minus j sine omega k. And when we substitute this Euler's identity, we have for k equal to 0, we have this value 1, which is we convert into polar forms, magnitude 1, phase 0. And then for k equal to 1, we have this value negative 1 in the magnitude and phase. The magnitude is 1, the phase is negative pi. So we have this one for w0, the magnitude is positive 1 at this point. The value is positive 1 at this point. The magnitude is 1, and phase is 0, so at this point. For W1, the value is negative 1, so at this point, negative 1, the real numbers, and the magnitude is 1, and phase is negative 180, negative pi here, okay, negative 180. Or we also can rewrite this one as positive 180 at this point. So when we substitute this value of w, k for 0 and 1 into this equation, so xk for k equal to 0, so x0 equal to g0 plus this one is 1, so we have positive sign here, multiply with h0, which is equal to x1. For k equal to 1, so x1 is equal to g1 plus this factor w1, which is negative 1, so we have this minus function here, multiply with h1, which is equal to x1. Basically, the Radix 2 FFT algorithm consists of taking 2 data points at a time from memory, performing the butterfly computations, and returning the resulting numbers to memory. Okay, so when we convert into butterfly signal flow graph, okay, we have this node representing the xn, x0, and x1, and this is xk for x0 and x1. For x0, since g0 equal to g1, so this is x0, which is equal, and this is from this node, this is also x0. And then from this node x1, this is x1, and for this part, since it has negative 1 gain, so you should multiply this signal x1 with this gain negative 1, so it becomes negative x1. x0 is actually equal to g0, and also x0 is actually equal to g1. Since we are calculating this one for k equal to 1, so we should use g1, and when we're calculating for k equal to 0, we should use g0. While for this one, x1 is equal to, actually the answer for h0 and h1. So for k1 we use h0. So for k0 we use h0. For k1 we use negative h1, since this is negative x1. So this node is for addition process for this function, for this signal and this signal. So x0 equal to g0, okay, this one, plus h0. In this case, based on the equation, x0 is equal to g0 plus w0 multiplied with h0. In this case, from the previous calculation, w0 is equal to positive 1. So we just leave it, the lines of this between this node as this one, without labeling as positive 1. That's okay. And then the next one is x1 is actually equal to g1 multiply with w1 plus w1 multiply with h1. So since w1 is equal to negative 1, so we label this line between these two nodes as negative 1, representing w1. That's why this w1 will be multiplied with h1. So we have negative h1. So for x0 is equal to g0 plus w0 multiplied with h0. So we have h0 here, since w0 is 1. And for the next one is x1 equal to g1, this one, g1, x1 equal to g1 plus w1 multiplied with h1, which is negative h1. So x1 equal to g1 minus h1. So the basic computational units of FFT shown in this figure is called a butterfly, okay, based on this line that connecting between these 4 nodes. Okay, this is a butterfly pattern. This structure may be simplified by factoring out a term wkn from the lower branch. In this case, x1 is the lower branch. The complex exponentials, okay, this one, where this is actually equal to the complex exponential, multiplying with hk, are called twiddle factors.